Okay, we are still waiting for some students. Okay, I think the number, there's still maybe 10 students. We will wait for maybe 1 more minute. Yeah, we do have a lab today. Okay, so we will have the lab for you to demo your programming project to TAs. And in the meanwhile, if you have questions, you can ask the TA. Yeah, we do have the lab. Okay, I think you're welcome. I think yeah, we cannot wait longer. Okay, let's begin. And so last time we see this MAC protocols, right? So we mentioned that the reason we need these protocols is because in the subnet, okay, inside the subnet, usually people are connecting to the same media. And if one person is talking, the other person is also talking. None of these two people will be able to recover any message, okay? So we need a mechanism to let only one person talk at a time. But when no other people is talking, we want to let that person talk as long as possible, right? So here we are using, analogy, right? So this is a really, not person, it's really hosts, right? The network interface card, but it's kind of similar, right? So we talked about several protocols that you should be aware of, right? The first is Aloha. We analyze that Aloha's efficiency is very low, only 18% at the peak, right? So, which means in the best case, you can only use 18% of your bandwidth, okay, which is very low efficiency. Another method is called slotted Aloha, right? This will double your efficiency to 37%, okay? And we also have the other two methods really for wild environment. Okay, these two are for wireless environment. Okay, these are for wild environment. One is called the carrier sense multiple access, CSMA, right? Because you can sense the media because it's maybe the same wire, okay, the same piece of metal in light speed. So you can listen to the uh, you know uh, listen to the wire and see how things go, right? If it's busy, then you can avoid sending things, right? And the last one is called, CSMA-CD, right? So, you detect, right? So, and so here's the difference is that if you can listen to the, media, right? So you only transmit when your channel is idle, right? Because if somebody is talking, you don't talk, right? So this is the analogy, okay? So the next one is something like, so collision avoidance is saying that if I'm talking, right, but then I also notice somebody is talking, right? Here I don't even talk when I hear somebody is talking, right? But if I happen to already start talking, but I hear somebody also talking, right? I will stop my talk. I stop talking, okay? Because if both people are keeping talking, right, so no one can understand what's the content, right? So these are the difference between these two. And the next one is, let's continue. So last time we see that Aloha protocol, right? So the idea is very simple. So here Aloha and slotted Aloha are really for wireless environment, like radio, right? So we can broadcast stuff to B, right? And A can send stuff to B can send stuff to A, and but what happens if both A and C are sending stuff, right? Like talking, and it takes some while to reach B. And by that time, B actually hear both messages. Okay, so B receives both packets. Okay? Then B cannot get the actual data, right? Either data. Okay, so we call this as a collision, right? So the protocol is very simple, right? So Aloha just if you want to talk, you talk immediately, right? Okay, and if the other person say, hey, I cannot hear you, right? So because the receiver needs to acknowledge the packet, right? And for a while, right? So, and then you need to notice that maybe your message is not delivered. It's like you cannot hear, right? You cannot hear. When you talk, the other person can hear, right? And if you cannot acknowledge, then you need to retransmit. But before you retransmit, you need to wait for a random time, right? Because if two people are talking together, right, and then collision happens, and then they wait both for the same piece of time, right, amount of time, and then talk again, then there will be another collision, okay? We use randomness to avoid a second collision, okay? Of course, there could be a second collision with very, very low probability. In that case, each one will then back off again using a random time. And then the third time is even lower probability, right? Because different samples are independent, okay, when you get a random time. And we will see how to get the random time, okay? So this is a simple method, right? And it's really good if you only have, a few senders. Right? Not many people are using this medium, right? Because you can keep talking if there's no, no collision. You just keep receiving acknowledgement, right? So this is actually very good. If not many people are using it, but if a lot of people are using it, you are in trouble, right? On the other hand, if you use this kind of channel division method like TDMA, right? You have very low utilization, even though other people are using it, right? Because you can only talk when at the time slot that is assigned to you, okay? Maybe 1 in n, where n is the number of people talking on the same room, right? Okay, so this is a TDMA, right? There's also FDMA, which is frequency band, right? So how fast you can talk, right? So you can only talk with a limited speed while other people are talking, right? This is another way of division the results, okay? Channel results. Okay, let's continue. So this is the difference between TDMA and Aloha, right? So if you have very few people using, Aloha is perfect, right? So you can just keep talking, right? And TDMA, you cannot keep talking. You can only talk in a allocated slot, okay? On the other hand, if a lot of people are talking, and TDMA perfectly resolving these issues, right? If everyone has a lot to talk, right? Then you take turns to talk, okay? There's no waste in any manner in the bandwidth, right? There's only waste if you have nothing to talk, right? Then you wasted this slot, okay? But Aloha is in big trouble because you have all kinds of collision, and then you have to wait and then retransmit. Okay, so this is not ideal when you have a lot of people using, right? So these are the two extremes. If you have infinite number of data to stand, right? So you can use TDMA. It's the highest efficiency, right? But you probably know that most of the time you will be idle, right? And a very small fraction of user will be using the channel. Then Aloha is the best. As we said, Aloha frame has a problem. Right? So if you start transmitting here, that's still fine. Let me see. If you start transmitting here, that's still fine. But if you start transmitting here, right, your frame will have overlap. Okay, then this information of both frames are kind of corrupted. Okay, but you can all the way go to here. If you transmit a packet here, still you have some data corrupted with the other frame. Okay, so the only way you can do is basically saying that you can go from here, right, before here, or after here. Okay, so basically you have to, you have the collision domain is 2 frame size. Okay, right. So this is not ideal. So a solution for this is, as we discussed, right? So you can use slotted Aloha, and this simple slotting idea can double. Basically, it doubles your, peak utilization. Okay, actually, it's even better if your load is higher. Right? So almost Aloha doesn't work anymore, but slotted Aloha is still okay in some sense. Okay? And here, so these are the numbers. And the last time we do some analysis, right? So why this is, 37%, right? It's a 1 by E if you still know. Okay. And so Aloha is only half of that, okay? Because you have more collision. Slotted Aloha is saying, hey, because everyone has a clock, right? You can only talk at the beginning of a slot, okay? Right. So you can only talk at the beginning of a slot. So when you want to talk, you can observe whether other people are talking, right? Maybe you don't know because the previous slot, no people are talking, you will talk, but somehow another people are also talking, right? And then you will have conflict, okay? but you only conflict in one slot. But the next slot probably it's fine. You can send it. Okay, so the collision is only in one slot rather than two slots. That's why the throughput can double. Okay, but the problem that there's also a trade-off, right? So in Aloha, when you want to talk, you just talk. Okay, but in slotted Aloha, what you have to do, you wait till the beginning of the next slot and you talk. Okay, so there's some latency, cost there, right? Okay, next let's look at Ethernet. So now we are moving to basically the wide environment, right? So, and we said that there will be a preamble, which is delineated different frames, right? Ethernet frames. Okay, so we will use 10101010 because we know that we don't want to have long runs of zeros or long runs of ones. Okay, so we just have this. This is perfect for checking the preamble, and then we want to say, hey, now I should stop. Right? So then the eighth byte is actually 10101011. Okay, then if this is 0, means, hey, you should still wait for 1 byte. If this is 1, then hey, this byte is the last byte. Next is the content. Okay, then you will have source destination, right? And as I said, you think about a shared media, right? So nowadays, Ethernet is no longer a shared media. Okay, or we can say switch, make it a more better result. You can still regard it as a shared media, but there's no, no conflict, right? Two hosts can talk together without conflict. Okay, right? And as long as your destination is different, of course, right? So, so this is so this is how the Ethernet frame look like. Right? You will say, hey, who I'm sending to, right? And then you put on the same piece of wire, and everyone will get this frame, right? And they will say, hey, whether destination is me. If it's me, I will receive it and put it into the upper level protocols, right? Otherwise, I will just ignore it. Okay. Extreme case is, this MAC address. Okay, this MAC address, FFFF. These are all 1 bits. Okay. If that my MAC address is this, destination address is this, then no matter what the frame is, I need to receive it because this is a broadcast channel, which means I'm sending to everyone in the same, subnet. Okay, so everyone should get it. And we also have, other things, right? So we then have say how many bytes we have, right? And these are the bytes of the payload, the data. Okay. Then we will have a padding, right? So we will have padding. Okay. And finally, we need a checksum just to make sure these data bits are correct. Okay. The padding is necessary because we have a minimum packet length of 64 bytes for each Ethernet frame. You cannot be smaller than 64 bytes. Okay. We will see why this is necessary, right? So we will describe it later. So give it intuition. Basically, if you talk, right, even though it's light speed, but you can still consider the other side will take like 1 nanosecond, for example, take some time to receive it, right? Okay, and if your frame size is too small, maybe the other side cannot hear it, right? So and he will talk, and then you will have 2 signals transmitting on the line, maybe in opposite directions. Okay, actually it's corrupted, but you cannot detect it, right? So then we are in trouble because this is a CSMA, right? So carrier sense, right? So you need to be able to sense, hey, somebody is sending, okay? And there's a light speed delay, okay? If your wire is long, okay? And basically that's it, right? So again, so these days I would like to emphasize Ethernet structure is different, okay? In the old days, everyone just using a T connector, right? So connect them into the same piece of metal. Okay, this is why, right? And then you can send the signals, right? There's a terminator, means there's nothing there. Okay, you can also have a repeater, which means maybe the signal is very weak when you send from here to here, right? So you want a repeater, so you can expand this network a little bit, right? Maybe your subnet should have 50 machines. You want to have 4 machines right now. You can use a repeater to expand it. Okay, so we weaken the signal. All right, so here's how it works, right? If you put some data on the wire, right, in light speed, it will reach all the hosts. So all the hosts will reach the data. Okay. So this is, for example, like those terminator and repeater, this kind of very primitive devices, right? Structure is 10 base 2, right? So this is actually the terminology for I think 10 megabyte per per second, very low speed connection. Okay, and later, there's a new Ethernet design. So we have the hub. Okay, if you still remember, so you don't have to use the T connector to connect to the Y. Okay, right? You can use a hub. What hub does is that it will broadcast a message to the other machines. It will not broadcast a message back because it's meaningless. So this signal is already here. Okay, and so because it's broadcast, right? If you have two hosts sending things, both will be broadcast. Then you have the collision. Okay, so you can think they are still in the same piece of metal. Okay, right? So like the Y. Okay, but it's more convenient because you can connect stuff, right? You can connect stuff in the hub. Okay, you don't have to use T connector, and it's more easy, right? It's easier, right? So you just have a wire to the port in the hub. Here you need the key connector and kind of disconnect to host and then plug in here. Okay. But both devices are actually, at the physical layer, not even the link layer. We are talking about the link layer protocols, right? But these devices are at the physical layer, right? Because you think about it, it's just the functionality of like a piece of metal, right? So it makes the signal connect to the other side, right? So there's no even if this guy is sending to this machine, you also send to this machine, right? So it's like the same medium. These wires are binding together in some sense, right? So this is really like a physical stuff, right? It's not even handling the data link frames, okay? So hubs and repeaters are layer 1 devices, which means it's the lowest layer, physical layer, right, device, okay? And now they will have new protocols, right, using this hub structure, right? Because you need these wires to connect, okay? And these wires are twisted pair, so with crystal pad, right? And you can plug one side into your network interface card, the other side into the hub, okay? Right, so there are different speeds, right? This is 10 megabits per second. This is 100 megabits per second. The T means twisted pair. Right? So again, this is I think you can still buy hubs these days, right? So, but it's relatively outdated. Usually now we buy switch, okay? And this is totally, I think it's totally retired, outdated, okay? It's obsolete, no one uses it. And so, yeah, let's look at what people can do, because you see this is a piece of metal, right? Everyone talks, and light speed you reach everyone else, okay? So how can we how can we do the MAC control, right? MAC protocol, okay? So this is a little bit different from the wireless case, because in the wireless case, you cannot send and receive in the same time, okay? Your transmitter, if you're sending, it's very difficult for you to receive in the same time, because you are talking in the piece of air, right? So, and then you want to receive what other people are talking, right? So this will be very difficult. It will be cropped by your sending source, okay? But it's possible, right, in the wired connection, right? You just because you're connected to the piece of metal, you can really do this called carrier sense multiple access, right? Which means you are sensing this wire, okay, and to see whether there's a collision, okay. So the key inside, for example, if you are sending 1 bit and you 0 bits and you detect 1 bit, right? So of course there's collision. Okay, you should stop talking. Okay, so there's a way to do collision detection. Okay, using Ethernet, using wired connection. Okay, the key insight really is that wired protocol allows us to sense the medium. Right. So the algorithm for CSMA CD means collision detection. Okay, is this right? So we will first sense for carrier. Right. So on the wire we will sense it. And if there's some signal carrying on the wire, we will wait for it to end, right? So this is like if somebody is talking already in the room, okay? You will just wait for the person to stop, okay? Finish talking first, okay? So then, this is making sense because if you send something, right, it will cause a collision and just waste time, right? If somebody is already talking and you talk and the other person, when you know that he will not stop talking or she will not stop talking, right? Then you will just let him or her finish his sentence, right? Okay. And then you will then send the data frame, right? Because now it's idle, right? Because you wait for it to end. Right? Of course, if this is if branch, else means that no one talking, then you also send a frame. Okay, and then when you send, you can sense for collision, right? Let's say you send a 0 bit, but somehow when you sense it, you get a 1 bit, a high signal. Then there's some issue, right? Some other signal is also flying on the wire. Okay, and if that's the case, then so this is step 5. If there's no collision, right, whatever you send is also where you listen, right? You hear. Okay, in that case, the frame has been delivered. It's fine till the very end. Okay, if any point of time in the middle, you find some bit is not what you sent, right? So then you need to abort immediately. Okay, because there's a collision happening. Right. So this is also makes sense, right? Because let's say you start to talking, right? But there's some other people in the room who don't care about you, and then they speak again, they talk again while you are talking, right? So if both of you are continuing talking, then both of you are in trouble, right? So no one can get the information, right? So what you will do is hey, because the other person is talking, right? I just abort, okay? Right? I stop talking, for example, right? And because if you keep sending stuff, right, it's the content is corrupt anyway. Okay, you need to retransmit anyway. You should stop. Okay, right. So this can happen, right? So maybe the other party is not so polite in some sense, right? But here, if everyone is running the same Ethernet protocol, right? So this will not happen. Right? It's just that it's unfortunate that both of you start talking at the same time, and it take maybe 1 nanosecond of light speed to reach the other side, so the other side can sense it, right? Right. So and then because when you talk, you definitely will not detect anyone talking. Okay, but when you start to talk, right, it's possible the other side is talking. That's because maybe Alice is talking because he cannot hear Bob is talking. But when she start to talk, Bob's voice is propagated to Alice now, right? Because when Bob starts to talking, Alice's voice has not reached Bob yet. Okay, even though it's light speed, there's some difference, right? This is really to handle this boundary case, right? If both of them talk almost simultaneously, then they cannot hear each other at the beginning. Okay, but then after a small amount of time, right? Like we know the minimum frame size, right, for the light speed propagation. Okay, right? They hear each other is talking. Okay, then both of them will be politely back off. Okay, so then they each get a random number. Okay, right? I talk after 2 seconds, you talk after 10 seconds, right? And then it can just work out. So this is a analogy of the meaning of this protocol. Any questions? If not, I will continue. So collisions can occur, right? So as we explained, why? Because two people may talk at the same time. Okay, two hosts, will send at the same time. Okay, and the collisions are quickly detected and aborted, right? So this is the key, right? If unfortunately both hosts are sending together because they didn't receive any information from the other side, right? They talk at the same time, for them. Okay, and then both will politely back off, okay, and wait for a while and talk again. Okay? So this is detected and aborted very quickly, right? You will not waste time talking while other people are also talking, and during this period of time, the information are garbage. Okay, and please know that there's a role here. We will cover that in a later slide. Okay, so how far away, like your y is from one host to another, right? That decides your propagation delay because there's still a speed to propagate the signal in the y. Okay, and so because when you talk, you may not detect other people's talking, right? Let me use a picture to illustrate the idea. For example, Alice is talking, and this is a piece of wire. Okay, you're talking, and Bob somehow is also talking, right? The Alice is the signal is propagating slowly while Bob is slowly. Okay, and the Alice reach Bob, and Bob maybe reach Alice. Okay, right. If that's the case, then Alice find, hey, Bob is talking. Right? I should have Bob. Okay, right. So there's a requirement that you should be able to, when you start to talk, you should be able to talk for a while. Okay, till Bob's voice reaches you. Okay, That's why we need a frame size, right? So we need a minimum frame size. If I send too quickly, something like this, right? So keep in mind the frame has some time to put on the wall, right? So while I'm still putting the frame on the wall, Bob comes, okay? I will drop the whole frame and wait and send it. Right? And this is the light speed to reach Bob, okay? But another extreme case is this, right? I put the frame is small. Already put it totally on the wall and then propagate to Bob, okay? Then you cannot abort the frame because it's too late. It's already out, okay? So we need a frame, minimum frame size. So even then when Bob reaches you, okay? Then you are still putting this frame on the wall, okay? Then it will not be too late to abort. Any questions? Yeah, I hope these examples will help you understand this protocol. So again, if you remember, right, so if both sides detect the collision, right, they need to back off, right? So we use an exponential back off strategy. Let's see how it goes, okay? Firstly, if the sender detects a collision, right, it need to send a jump signal, like all 1 bits, right? So tell everyone, hey, there's a collision on the line, okay? Everyone will see the jump signal, a bunch of ones that is very long, for example, a special token, right? They will just know that there's a collision, okay? And not to continue to listen to that packet, listen for that packet, okay? And so this makes sure all hosts are aware of the collision, right? So, and the jump signal is 32 bits long, right? So, of course, there's a header overhead, right? So this jump signal itself is the Ethernet frame, okay? And after everyone receives this signal, right? So this signal should be very robust because maybe the channel is still quite noisy, right? So it's like all 1 bit, right? Everyone can get this jump signal, okay? And then everyone will just go back to the exponential backoff, right? So which means everyone will wait after being aware that the channel is kind of noisy. But say if the host still need to sense stuff, it will wait. Okay, but everyone should wait for a different amount of time. If you wait for the same amount of time, then you talk at the same time again, and you have infinite loop of collision, right? So the backoff operates in multiple, half a kilo bits. Okay, so this is a 512 bits, right? So this actually, why we have this number, okay? So this is actually depending on the bandwidth of the connection we are talking about on the wall. Okay, we'll see that later. Okay, just keep this number in mind. 512 bits. Okay. So as we said, we want to sample a random time in the slots, right? So we don't want to, people to wait for the same number of slots and then talk again. Okay, so you should wait for 2 slots. He should wait for 3 slots. Then there's no collision, right? Even if you are talking starting from the 2nd slot, the 3rd slot, the other party, if he decides to talk, he will not talk because he can sense that you are talking starting from the 2nd slot. Okay, so let's see. So there will be a range, right? You randomly sample number from slot number from which is k. Okay, so here is a range is decided on n. Right? N is the number of collisions. It's like if you the first time you collide, you will get from 0, 1, 2. Right? So 2. Okay. The second collide from 4. Third time collide 8. Right? Then 16, 32, etc. Okay, double. The reason we want to do this is because, if you wait for a small amount of time, but a lot of people are there, right? So the collision probability is very high. Okay? If you try once and you fail again, that means a lot of people are talking. It's kind of busy on the wire. So you want to wait double the time. If still so busy, you want to wait for another double the time. Okay? Until sometime you can really get an idle channel in the sense that, right? So this is the idea, right? And because of the, reason, if you send beyond the minimum packet size, right, you will not be interrupted because other people are sending, right? Because other people should already arrive you if you send at least this amount of bits. Okay, as we said, 64 byte. Okay, 64 byte times 8, right? Each byte is 8 bits. It's exactly this number. Okay, there's some reason. So that means if I have a very big content, I'm sending a big frame, right? Either I abort just about the beginning of the frame, or I don't abort, right? Otherwise, if somebody can talk in the middle and you're about it's wasting, right? So you waste a lot of bandwidth to send already because the whole packet will be dropped. Okay, this part will be wasted, but this cannot happen. So we need to wait for at least at the unit of this amount of time, okay? At least a 1, right? Because after 1 and if other people are talking, we should already hear it. But we will choose a random number between these. Okay? So each time we will double. Okay, so that means 2 to the power n. N is the number of collisions you already have. Okay, and the time you wait is k times this number. This number is how long it takes to send 1 slot, right? And then you have k slots, okay, of data of the waiting, right? So you wait for so many times. Okay, so if you want to see what's the Ethernet bandwidth we're targeting, right? So it's very easy. Okay, so you can see we have 512 bits, right? To send this is equivalent to using this amount of time, right? 51.2. I think this is US. Like, I think it's in 10 to the power of -6. Okay, right. So millisecond. Okay. This is what? How do we call this? Anyway, this is 10 to the power -6. Okay. And yeah, millisecond. Right. MS is microsecond. Okay. Right. So it's 10 to the -6. This is 10 to the power -6. Okay. And this is divided by this is 10. Okay. So this is 10, but this is 10 to the -6. So if you put this up there, it's 10 to the. Okay. So we are saying that the bandwidth of the Ethernet we are looking at is this amount, right? So you can write this as you have 10 and then six zeros, 3 zeros, 3 zeros, right? And this is k, this is m, right? It's 10 m. Okay, so this is targeting 10 m bits per second Ethernet. Oh, so how is this true then? This is true then based on bits, right? So this is the number of bits, okay? And if you are because we are talking about 10 megabits per second, right? According to this speed, this bandwidth, sending so many bits will take this time. Okay? To answer your question, so we are reversing computing it to tell you this time is true then targeting this speed, 10 to the 10 to the power of 7 bits per second. Okay? To answer your question. Yeah, if you have, I didn't answer your question, just let me know. I hope this. So basically, so we are waiting in the unit of so many bits, which means in the unit of so many times, right? So this is the time that people are putting packets on the wire, right? So this stuff on the wire. Okay? If you wait for so many time, which means so many of those packets time, okay? So many for k times that so many bits can be transmitted. Okay. All right, so. Another thing is that we cannot continue, right? So because this is exponential growth. If you look at the 2 to the power of something, right? 2 to the power of 10 is 1,000, but 2 to the power of 30, for example, right? It's 1 billion, right? So it's increasing fast. Okay, so but beyond a certain amount of time, it makes no sense, right? So let's say if you send a packet, you need to wait for 10 seconds. It makes no sense. The collision is really low, right? Okay, it's probably just because of some other reasons. So in that case, we will cap at 10. Okay, so if you fail for 11 times, I'm still waiting for this 10. Okay? And 12 times, still wait for 10. And until you will reach 16 collisions. Okay? After that, you will just drop this time, okay? Because this frame cannot be delivered. The channel has some issue, right? Too many, like there's some jams or some tags. Okay, someone may not be following the protocol. This is kind of one example. If everyone's politely exponential backup, then this should not happen. And so the backup time is divided into contention slots, right? So each slot is 1. So you have this is like 2 to the power n minus 1 slots, and you pick a particular slot. So Ethernet is still slotted. Okay, there's a clock. Okay, now let's explain a little bit why we require the minimum packet size to be 64 bytes, if you remember, right? So we said if there's no enough data, you need to pad. Okay, usually pad with zeros. And it doesn't matter because before your data payload, you have a length, right? You know how many bytes are useful. The others are just for meeting this minimum packet size requirement. Okay? So this, again, why we need to have a minimum size requirement. Because if we don't want to send a 64 bytes, I just want to send 2 bytes. I still need a frame of so big one, right? Why? Okay? This is to give host enough time to detect collisions. Okay? So that also tells you that if you send small, like send an integer, right? So like a structured integer, 2 bytes, again. Actually, you are sending 64 bytes again. Okay? But don't worry because the down there usually the application will batch them and send using a message queue, right? So unless like a timeout, then with avoid too much latency, it will send. Okay? Usually they will try to batch and send to the destination. The message queue to destination. This again at the application level. Okay? If you directly work on a very low level, right, so it will be very inefficient, right? So you need to use 64 bytes anyway. Okay? So why it will give host enough time to detect collision? Actually, we already covered that, but here there's an animation that gives you a better idea. Okay? So what's a relation between the packet size and the cable length? So there's actually a relation between them because the longer your cable length is, even its light speeds take longer time to reach the other side. Then after you start talking, B haven't detect you, right? Because it takes your signal to reach B. So B also start talking, right? And by that time, both of you are colliding. But if you finish putting the packet on the wall, then you cannot recall it, right? So you should have, when B reach you, should still be putting your packet onto the wall. Okay. So here's the animation showing this. Let's say at time t, host A starts transmitting, right? And there's a very, very small propagation delay here, right? But before you reach almost after time d, almost that B will listen, hear it, but right before you hear it, B also send out back, right? So B sends data. It's not exactly this time. It's exactly t plus d. It's already reached, right? Let's say minus epsilon. Okay, you can think of things like that. Then B sends some stuff and on the one, and then A will get it in t plus 2d, right? So because B signal also takes d time to reach. Okay. So by this time, A should not finish putting the current frame on the wall. Okay, it should still be putting on the wall, so it can record the frame, right, by sending jam signals. So in order to do that, we need to calculate something, right? So you think about this, right? So this propagation 2D, right? So it's like twice the while. Okay, first you propagate there, but right before you arrive, you also send something, and that signal will reach you, right? So it's like twice the cable length. If this is cable length, okay. So this divided by 2, you can move this 2 to here. It's like twice the cable length. Should be what? Let's think about if you have the light speed, you can divide it by light speed. Okay, divide by light speed. Okay, this is the time passed for 2D. If you aware, right? So how long it takes for A signal to reach B and B happen to also send something and then reach A. So this is the time. Okay. For this time, A should still be putting your packets on the wall, which means your minimum frame size should be long enough that you divide it by the bandwidth, by how fast you can put the wall. Should be equal to this time of a round trip, right? So this is how basically this formula is telling you how to calculate that. Right? So the frame size, we know it's a 64 byte, okay, which is times 8. I think this is not very clear. Push this up a little bit. Yeah, that's good. So here as we explained this formula, why we want to use this formula to compute, right? Now we know that so this is the frame size. We know that we have so many bytes, but we are talking about bits when we do that here. Right? So we will type 8, and this we have so many bits, right? And light speed is 3 times 10 to the power 8, right? And meters per second. So but we cannot do that, okay? Because it's the medium is not empty, right? It's not an empty space. Okay, it's still there's some block in the maybe molecules, atomics. Okay, okay. So we will be a little bit lower than light speed, right? So, and this is the light speed. This is the frame size. Okay? And divide by 2 times the bandwidth. Right? So we know that the bandwidth is 10 megabits per second, assuming this is the target Ethernet. In the other case, we can compute the maximum cable length allowed to be, 6K meters. Okay, which means if you want to connect a few hosts, right, and you are using this protocol by default 64 bytes, then your length should not be longer than so many meters. But this is a really safe, safe value, right? Because you think about even a data center room, maybe this is not a small number. Okay, so this is safe. They purposefully choose this cable length to be very safe to compute this number, so that you will always, while you are putting a packet and somebody having to hear you initially send some packet, you will finally got it before you put the whole packet on the wall. So this is the idea. Is this clear? I hope this is clear. Okay. Yeah, there's a question. There's no repeater. Okay, there's no repeater. You can have a repeater, by the way. Okay, for example, if this is so long, I believe you need to have a repeater because a sending signal is weaken, and then. But here in this example, we are not considering repeater in our context, right? So you can add a repeater in the middle, but we assume that after repeater it's the same piece of metal and signal is strong again, so they can listen to the bits. Okay, so you can put a repeater there, but when we compute this, we don't need to put in more factors here. Okay, I hope I answered your question. Again, no one will use so long. Why? Okay, so again, I want to emphasize that this is for 10 megabits per second, right? So this is 10 megabits is this m is 10 to the power of 6, so 10 m is 10 to the power of 7 BPS, right? So this is really targeting a very low speed Ethernet. Now these days we use 100 times faster Ethernet by default, right? 1 Gbps. Okay, and so the packet and the cable length should change, okay, for faster Ethernet, right? So of course, if you can put things on the wire faster, your frame should increase proportionally, right? Proportionally in order to not finish, okay, when the other piece signal comes. Okay, so you need the minimum packet size should increase. All right, so let's finish this slide and then let me see what's the next slide. Let me see. Okay, let's finish this slide and then we'll take a 10 minutes. Okay. So if you remember, right? So we have a backup time, right? So and it's in the unit of so many bits. Okay, right? And if you memorize that, we have the Ethernet packet size. It's also so many bits, right? So because we say that the minimum Ethernet packet size for 10 Mbps, Ethernet is so many bytes, which times 8 is so many bits, right? So is this a coincidence? It's actually not, right? So because when you wait for at least the smallest unit is so many bits. Okay, if you wait less than this bit, the standard, send stuff and they finish, right? And the other party reached its clock, right? So but you don't recall it. Okay, so that's the issue, right? So you need the backup time that you wait should be also the unit of you will be able to hear the other part. Okay, so because if you have less than so many bits while you are waiting, right, and another people send, okay, but because you wait for less than this time, right, so you send again, right, then you guys can collide. But if you wait for at least this number of bits, right, this signal from Bob will already reach you. You know whether you should send or not because you can listen to the medium. So this is the reason that we have, back of timer, right? So each slot is so many bits, okay? And we sample k times, k number randomly, and k times is slots for waiting. Okay, I think we will stop on this slide and we continue next Monday. And I will take a short attendance. Okay. And we still have lab for today. I think we have the Canvas link. Let me get it. Okay. Nisa, am I pronounced correctly?
Yes, I'm here.
Okay. Right. So let me see. Alex, are you here? So I see a student asking, are we just presenting if we are done with? Yeah, you demo to the TA, okay? Because I remember there's like a 50% of the score for you to demo each step to the TA, okay? So you need to demo to the TA, and after that you are done. Okay, so you, right. So in the lab you need to demo to the TA what you did, and then TA will give you a score. Right. So let me see. Okay, Alex. Are you here?
Yes, I'm.
Okay, thank you. And Quinton, are you here? Quinton?
I'm here.
Okay. And Matt, are you here? So I will stop answering questions and finish. So I don't want to delay ever. Cass, are you here? Cass?
She's
No?
here. Check the chat.
Hello?
Yeah,
Check
Cass
They
is
said
here.
they're here in the chat.
Oh, okay, I see. Okay. Okay. Karin, are you here? Karin?
Yes, I'm here.
Alex Hinkle, are you here?
Yeah, I'm here.
Okay, thank you. Cameron, are you here? Cameron Jones? No? Let me see. Jialin King, are you here?
I'm here.
Okay, thank you. Trina Ling, are you here?
I'm here.
Thank you. Let me see who is not here. Andrew, are you here?
I'm here.
Thank you. Let's go faster. Darian, are you here?
Here.
Okay, thank you. Raj, are you here?
Yeah, I'm here.
Thank you. Let me see. Carlos, are you here?
I'm here.
Thank you. James, are you here? James? No. Okay. So Angus Wong, are you here? No. Let's go to the next list, and I think if you are from 334, then that's the end of the.
Dr. Yan, did you call my name?
I think.
Cam Jones.
Let me see. I probably call your name. Let me see. I do remember. Yeah, so you're here, right? Okay.
Yeah, I'm here.
Okay.
Thank you.
James and Angus, if you are here, let me know. Right, so let's do a fast sampling for this list. Okay. Next time we'll reverse. Ebony, are you here?
I'm here.
Okay, thank you. And Stiller, right? So Stiller, are you here?
Skylar.
Skylar, sorry.
Skylar, I'm here.
Skylar, sorry. Yeah. Okay. And Jessica, are you here?
I'm here.
Okay. Megan, are you here? Megan?
Yeah, I'm here. Sorry.
It's okay. Rishikesh. Rush.
Yes.
Okay, thank you. Let me sample the last. Okay. Lindsay, are you here?
I'm here.
Okay, thank you. So that's all for today. Thank you. Have a nice day. I will see you next morning. Bye. And I will be here if you have any questions. Feel free to ask.
Are we having lab today?
Yeah, we have lab. Okay, so for this lab, I think the TA should make it clear already, right? So you need to demo to the TA, right? So we have 2 labs for you to have QA and also demo your project to the TA. Okay, and then TA will give you a mark. It's okay? Oh, again, so there's a student, Alex, asking whether we will be going over questions we might have, right? So yes, the lab is purposeful also for you to ask questions for the TA, okay? And then if you finish your demo to the TA will give you a mark, okay? If you have a question for me, you can ask now, okay? And I will probably disconnect after 1 minute. Luca, I didn't call your name, okay? I see the chat. Yeah, if you finish the demo today and you finish the project, you can skip the next one. Okay, but because there are a lot of students, we need to give 2 labs for demo. Okay. I hope I answered your question. Okay, it seems that there are no more questions. If you have any question, feel free to send an email.